Okay, so starting a new recording, there's probably be two links then that I'll send you to YouTube's kind of half and half, picking up where I had left off, discussing the three states of water and the three states of matter in general, solid, liquid, and gas. Gonna move forward from that because the state that we're interested in for this lecture and in life in general is mostly the liquid state, all right, even though there is definitely influence from the gaseous state and the solid state of water in life. Another characteristic that I want to talk about, another physical, chemical characteristic is the specific heat capacity of water, all right? Every substance has a specific heat capacity, which is the amount of heat essentially that they retain, that matter retains. And every molecule, every matter that we see on Earth has this capacity to retain heat or not. And water has one of the highest capacities for retaining heat. This also has an impact on life and has an impact on the issue of global warming. Metals, for example, typically have a low capacity of heat depending on the metal. In other words, they radiate heat out and they diffuse heat fast. But water is the opposite. It's like an insulator. So water obtains and retains heat. Heat is measured in joules. That's the unit that is used for measuring heat. And you can see here that it takes a little above 4 joules of heat to raise the temperature of water by 1 degree Celsius, all right? And so to raise the temperature of water by 1 degree, it takes a little over 4 joules. Don't worry about the units, it's just part of the physics of it. By comparison, for example, to raise 1 degree of copper, to raise copper 1 degree, all right, it takes about 1/10 of that, 0.385 joules, all right? We can round this off to 0.4. So from 4 to 0.4 is 10 times. So in other words, it takes 10 times more to heat up water by 1 degree, but also the water retains that heat, 10 times more than copper. So copper diffuses heat very fast. That's why they make for good pans. It transfers the heat from the stove, whether it's gas or electric, to the food rather fast. And it also cools down rather fast because it has a low heat retention, all right? But water has a high heat retention, and that has an impact on nature. A benevolent impact in general. So what it does for the environment is that generally what happens is that water stays warmer in winter and cooler in summer, so that areas that are near water will be warmer in winter and cooler in summer. For example, we have the experience here in Miami that if we're close to the ocean, it will be a little cooler in the summer, aside from the breeze, which also helps a lot because just water retains that heat capacity, all right? And so the same effect in the winter time up north, if there is a city that is near the water, it will be a little warmer or less cold, I should say, less cold than a city that would be inland. Of course, this gets overwritten, if you will, in the human experience by the wind, because the wind is strong or stronger than this passive heat capacity. So we may not feel that too much if it's windy, okay? It overrides the water effect, the humidity effect. All right, so anyway, moving forward, looking at water in its natural state, more on the planet itself, moving beyond the actual physical and chemical properties of water, we see that the temperature on Earth, all right, varies in that range, that 30-degree range in Celsius, which translates more or less roughly to a 60-degree range in Fahrenheit. As we move from the tropics, which is the warmer region, to the poles on opposite sides of the Earth, it's going to get gradually cooler, right, on both sides. And so that's another interesting property about our Earth as a whole, that at the equator, these are, this is actually, I guess it's infrared or something like that. It's the heat retention, the actual heat retention of the Earth. This is not painted over the Earth. These are actual measurements that portray graphically on a scale, on a temperature scale, and you have the two there, centigrade and Celsius and Fahrenheit, the amount of heat, the average amount of heat in a year on the Earth. And we can see that along the equator, of course, is the warmest, and then moving either north or south from the equator, latitude up or down, we get cooler. So that overall, we can talk about three regions overall, again, in the big picture, three regions of the Earth that of temperature on Earth, mostly along the surface of the Earth, right? And certainly within the upper mile or so, so definitely within the troposphere. Three basic areas: the tropical area along the equator, where we have a generally warm to hot environment throughout the year, to a temperate region, north-south, more or less parallels 30 to 60 degree latitude, okay, 30 to 60, equator being 0 degree, and the poles being 90 degree, either 90 degree north or 90 degrees south, right? It's a right angle. So if we move up along the surface of the sphere, we can have degrees, radial degrees from the hypothetical center of the Earth core. So 30 degrees, up to 30 degrees north and 30 degrees south, we have this band of the tropical region. Then the next 30 degrees, either north or south, generally, so from about 30 latitude north to 60 latitude north, is the temperate region, the same in the south. And then the last 30 degrees, either north or south, from 60 to 90 degrees latitude, north or south, we get the polar regions. So tropical, temperate, and polar, north and south. And seasonal wise, then in the tropical region, it's going to be mostly warm or hot throughout the whole year. And then the only difference that we'll see here is going to be whether it's rainy or not rainy. So we get the rainy season and the dry season. Let me stop there for a moment. Moving to the temperate region. The temperate region, either north or south, is going to be where we get mostly the 4 seasons, an average of 3 months each of the 4 seasons, because if we divide the 12 months into 4, we get into 3, we get 4 seasons, all right? So the 4 seasons that are distinct from each other temperature-wise, with all the effect that that has on nature, is going to be from about more or less from 30 to 60 degree north or south. And then the polar region from 60 to 90, where it's going to be mostly cold throughout the whole year, mostly cold. And so back to the tropic then, the difference here is going to be mostly on the amount of rain, whether, so it's going to be generally a wet season or a dry season. And the wet season coincides with the summer, more or less, and the dry season coincides with the winter. And that actually has a reverse effect on the temperature, because even though by geography, the tropic is going to be mostly warm or hot, being at or near the equator, all right? Temperature-wise, when there's rain, all right, especially heavy rain like the monsoon season, heavy torrential rain, bucketfuls of rain, what happens is that water, the rainwater going through the atmosphere, picks up heat, absorbs heat, all right, absorbs heat and retains the heat and kind of sinks, buries that heat into the ground when the rain comes down. But the rain is forms up in the stratosphere, the edge of the troposphere, right? So that rain, when it comes down, is very, very cold, and it heats up as it goes down into the ground. The bottom line is that it cools slightly, cools the environment, cools the atmosphere near the surface of the Earth, certainly within the upper mile or so, which is essentially where nature lives, okay? So the interesting phenomenon is that during the summer, it is a little cooler generally in the tropical regions than it is in the winter. And that is because of the rain versus no rain. So those are the two seasons, and then that has an effect on nature, it has an effect on agriculture, and also on culture. In other words, on the social life of these people who for millennia, centuries and millennia have adapted to the rainy season or the dry season being either cooler in the summer or hotter in the winter, okay? But that is because of the rain itself. In contrast, so I already talked about the temperate regions, north and south, which have pretty much the 4 seasons. But I also want to mention, in contrast with the south, you notice that the northern hemisphere is where most of the land mass is, okay? So most of the land mass on Earth, on the crust of the Earth, is in the northern hemisphere, as you can see plainly here, looking at the line of the equator, north versus south. So that means that most of the vegetation and most of the land animals are also going to live in the northern hemisphere, in contrast with the southern hemisphere, all right, where the temperate region is most affected by that, because then most of the landmass is going to be in that temperate region, which actually is a good thing because that's where we have the 4 seasons. So the seasonal variation from warm in the summer to cooler in the fall, to cold in the winter, back to cooler, to less cold in the spring, and to back into warm in the summer, you notice that that temperature gradient variation, which can be up to about 30 degrees Celsius or 60 degrees Fahrenheit, is going to occur in this temperate region, and therefore the plants and animals and even bacteria that live in this region have to adapt. They have to adapt in order to survive, okay? And so many species of plants and animals that live in the temperate region, both north and south, they have these circadian cycles, and they have these cycles in their own lifetime that are adapted on an annual basis to the spring, summer, fall, and winter. All right, both plants and animals. I guess in general, it begins with the plants by way of the season of germination, for example, which would be typically in the springtime when it's a little less cold and the rains begin, right? Showers, what is it? Showers of April makes flowers of May or something like that. Spring showers make May flowers, right? Both north and south. It's just that the big difference is that most of the landmass is on the north versus the south. And even in the south, when we get to South America, basically, which has the more substantial landmass in the southern temperate region, it's the southern tip of South America. It's not even the width of it, which is the Amazon basin, very tropical, right? But the southern tip is mostly Argentina and Chile, which actually goes all the way down to the Cape. And it's also mountainous region, So you're gonna get the vertical stratification effect that we talked about in the geosphere lecture, so that it's actually gonna get cooler than it would normally be, all right? So all this to say that the southern temperate region is not as representative as the northern temperate region. A drastic difference in the biota of the southern versus the northern temperate region, mostly because of the big expanse of land masses up here. Not only that, are also the relatively fewer mountain ranges. Yes, there are some mountain ranges, significantly the Rockies, and then in Europe, the Alps, but even the Himalayas are just touching it barely here, all right, which is another huge mountain ranges. And then there are other scattered mountain ranges that would have some vertical stratification, meaning cooler as we go up the mountain. For the rest of it, it's mostly plains and flat. Look at the Great Plains of the US, and then most of Europe is also kind of flat. When we get into Asia, Eurasia, is again fairly flat. Consider India, China here, which is a significant region of Eurasia, and a good part of Russia also. Here's Russia dipping down, even though Russia is mostly the Arctic, the boundary between the temperate and the Arctic region in Siberia here. Huge. Russia, I think, covers about 12 time zones away from the Bering Straits, close to Alaska, across going east toward, going west to, I guess St. Petersburg is near here, Scandinavian territory. Anyway, big contrast there between the north and the south temperate region. Then by the time we get into the Arctic or the Antarctic region, again, some differences because we have very little landmass in the Arctic, and I'll talk about the pole a little later on the lecture, whereas a significant landmass in the Antarctic, so significant that it's actually one of the 7 continents, right? One of the 7 continents, Antarctica, but it's totally frozen, at least up to now. In our more or less recent geologic history of a few thousand years, it is totally solid water ice, all right? And there are polar populations there of animals, but plants, no plants, because being liquid, being solid water, how are we going to get a water transport system into the plant? Impossible, right? So the only possible plants that could be in the area are going to be the algae around the edge in the ocean. Okay, so going forward, more could have been said, but let's move forward for the sake of time then. All right, back to, I want to point this out because this is going to set us up to understand erosion. Water is, the combination of water and wind are the 2 main erosion factors of the earth. And why is erosion important at the natural level? Because what's happened is that when the crust of the earth became cool enough to solidify from the magma, right, from the mantle, the upper mantle, then it started eroding. And even though the crust as a whole is thin, it has all these mountain ranges and plains and everything. So everything above the oceans on the crust of the earth has been eroding, not for millions, but for billions of years, okay? For billions of years. And it's mostly an effect, a combination of water and wind, And so the water is a tremendous erosion factor for this one property. Again, back to the physical chemical property of water for a moment. This is what happens. When water freezes, okay, into the solid state, which is known as a crystalline structure, so ice is a water crystal essentially, it actually expands. It expands. So frozen water expands, meaning it's less dense than liquid water. Of the 3 states of water, the most dense state is the liquid state, all right? So because this is what happens. When water crystallizes, right, when water freezes, the molecules become organized into this hexagonal shape, you see, where you have 1 hydrogen meeting with the negative region of the oxygen, the bold region that I'm calling it, and then the same for the next molecule. It doesn't matter whether it's hydrogen 1 or hydrogen 2, because these can flip around. You can rotate the molecule of water along its axis between the 2 hydrogens, and you can just continue to flip that around and rotate it and spin it, and it doesn't matter. There's going to be a probability of a hydrogen next to the bald spot of the molecule next to it, all right? And so when we arrange that, we get this crystalline structure, right? which makes for solid water. That's when water freezes, becomes solid. This crystalline structure is actually bigger. It takes up more space than liquid water when the molecules are slipping and sliding between each other. All right, because as you can see here, you can actually have two interactions going on between three molecules. You have the oxygen and hydrogen of two molecules, and then a third molecule can also interact with the oxygen of let's say molecule number one. So we got 1, 2, and 3 molecules interacting with each other, and so on. And you repeat that interaction story around, because now there's more heat. The molecules are more loose to interact with each other. Okay, and the end result of that is that water compacts a little bit when it's in the liquid state. Or the converse of that is that water expands a little bit when it is in the solid state, forming the crystals. So liquid water doesn't form crystals, obviously, as we know, it's a liquid state. But in the solid state, it is the crystalline structure, which is here. That, to the visible eye, what it forms is the snowflakes. And each snowflake is different. So why is each snowflake different, even if the crystalline structure of water is always the same? Well, because of the big difference is this, that this is pure water. This is pure H2O interacting molecules. But here, there are tiny microscopic particles of contamination. Dust or any other particle that's in the atmosphere is going to serve as a seed, as the core, to form that crystalline structure. And so depending on what that core contaminant is, will determine the shape, the actual shape of the snowflake, all right? All right, so these are actual photographs amplified, where you can see all the various different structures that will come out of water when it crystallizes, simply because the core, the contaminant, is a different shape to begin with. All right. This expanding action of water when it freezes, think of fall going into winter, especially in the temperate regions, okay? And especially in the northern hemisphere, when it's there's more landmass. When that water freezes, it expands, and the end result is that it cracks. It cracks the earth, it cracks the rocks, it cracks the boulders. Because in the fall, water will get in there, all right, liquid water, and then as it's freezing, the temperature is dropping, and in the ellipse, we're getting further away from the sun and so forth. And so what happens is that that water, when it freezes, water is also essentially incompressible. In other words, it is practically impossible to compress water, all right? Especially, well, in a solid state, but also in a liquid state. I'll tell you another anecdote about that in a minute. But you can see here clearly that this boulder, which used to be intact and had integrity, all right, has been fragmented by water seeping into the cracks, and eventually this seep was cracked by the water that seeped in there, froze, crystallized, and smacked the boulder open, cracked it into slices like this, okay? Now, when you repeat this action season after season, decades, centuries, millennia, millions of years, what the end result is that it pulverizes the rock, but especially in the temperate regions where water goes from liquid to solid state as it moves from summer to winter. All right, so we can say that the freezing, thawing action of water is more dramatic precisely in the temperate regions. In other regions of the world, what is more dramatic for erosion is just the passage of running water, of liquid water. And here I just show you a few pictures. Here is the Grand Canyon being carved out over millions of years by that river, okay? Is it the Colorado River, I think, that goes through the Rockies? And I'm sorry, through the Grand Canyon, and has carved out, this used to be a plain. This was a plain, which, by the way, is maybe about a mile to half a mile above sea level because of all the sediment that accumulated in the middle of the United States, what we call the Great Plains. They are flat, but they are actually above sea level as a whole because when the oceans were, the sea level was higher, 100 to 200 feet higher on average, deposited a lot of sediment there in the middle. Anyway, that's a different story. My point is that these are not mountains, these are canyons. And the difference between a mountain and a canyon is that the canyon has been carved out by a river from a flat terrain going down into the soil, okay? Mountain ranges are mostly from uplifting of the crust, especially when we are at the edge of a tectonic, of a continental plate, right? A continental plate, through drift and plate tectonics, the plates will push up against each other and cause mountain ranges to form, precisely like the Rockies, like the Alps, and like the Himalayas. But then through those mountain ranges, you get also solid water moving down, which also has a huge erosion capacity, a grinding of the mountain range, and these are glaciers. These are glaciers which also move, but very slowly. And it takes them hundreds of thousands, if not millions of years to move through mountain ranges, especially high up. And it is literally ice that is grinding the rock, especially at the edges and below the underneath at the base of the so the word just escaped me. Moving through this ice, moving through the rock, through the mountain range, always following gravity, being reactive to gravity. In other words, trying to move down glacier, and it grinds. But it takes them literally hundreds of thousands of millions of years to grind the rock, but it will. I don't know if you've ever been up in the Rockies. When you get a little bit up into the Rockies, you'll see what is known as boulder fields, and they're huge fields of boulders, rounded off boulders, like someone went there and sanded that down into this. It's like a bunch of marbles of different sizes and shapes thrown around, some small as the size of a marble, some large as the size of a house or a building. And those are boulder fields, which are typically is what's left over from the base of a glacier. When the glacier retreats or melts down, it leaves these boulder fields of ground up rock underneath, okay? Another one could be an estuary. In other words, when that river eventually empties out into the ocean, you can see the delta of the river expand like this in a ramification shape. Which is, again, erosion that goes on there, but also depositing a lot of sediment and actually building up the coast, moving outward into the ocean of sediment that is brought by the river, which is just erosion from the soil that was picked up either through a mountain or through a canyon and eventually deposited out into the sea. Another little anecdote about that one, in Italy, as I go from one slide to the other here, there's a port out away from Rome. In Rome, you have the Tiber River, the river Tiber that goes through the city of Rome. And below the city of Rome, the Tiber becomes kind of flat. There are no more rapids on it, so it's navigable. It's navigable from the ocean, from the Mediterranean. So one can navigate from the Mediterranean up the Tiber River up to Rome, the ancient city of Rome, okay? And so there was a lot of trade going on there. In fact, it's the origin of the city itself as a port. And there's at the port of the Tiber River, where it meets the Mediterranean, the delta is called Ostia. And there is Ostia Antica and Ostia Nova. Ostia means the mouth, so it's the mouth of the river, literally. So os, O-S, is an opening, like the mouth is an os, okay? So Ostia Ostia Nova, the new Ostia port of Ostia today, is about 1 mile, or rather Ostia Antica, which was the port of the city of Rome in the Mediterranean, is about 1 mile inland from today's Ostia, which is on the coast of the Mediterranean. 1 mile inland. In 2,000 years, essentially, the Tiber River has deposited about 1 mile of sediment from Ostia Antica to Ostia Nova today. There's another city nearby, which is also called Civitavecchia. Augustine was there with his mother Monica when they were returning to Africa, where they were from originally, after Augustine's conversion, and he made a bishop and returning back to his city of Hippo. So a lot of memories and religious Catholic culture there in the city of Ostia and Civitavecchia. Anyway, continuing back to erosion, here is shown in a graphic way the age of a river and the evolution of a river, all right? As it naturally carves out its way, what will happen with maturity, it will start meandering, because the young river will flow with rapid water down, following the path of gravity, So if you can think this is more or less of a plane, horizontal plane, like the Great Plains in the US, okay, before the Grand Canyon was carved out. And so the river flowed fairly straight, following the path of gravity, the line of least resistance along that horizontal plane. And as it did, it started taking away erosion, taking away soil from its banks, its sides, and bottom, all right? And as it did that, it started encountering some terrain that offer a little more resistance than other terrain. So again, following the natural pull of gravity, that river, that water is going to diverge to the soil that is least resistant, all right? So maybe there was a rock here or sediment that was more compacted, and so it followed naturally the line of least resistance, so it starts meandering. As the river meanders left to right and left to right, what will happen is that the opposite banks of the river meander even further, because as the water makes that turn around the river, around the edge, around the meander, okay, the curve, what happens is that the water out here actually it continues to erode outward. Okay, so it's an accumulating effect. As the river is meandering, it tends to meander even further and push further out sideways, carrying with it more silt, more sediment, more sand, more rocks downriver, okay, downstream. Eventually, when these meanders become large enough and old enough, they start breaking, because there's erosion going in here also, and they meet up and they can form islands. They can form islands. They can also form pockets of water that get deposited into ponds, or maybe at some point even small lakes and so forth. So a river has its own lifetime and life cycle, but this is just looking down on it at the horizontal level. It turns out that there's also a vertical dynamics going on as the river pushes down into, or erodes down into, it's carving its own pathway, right? And it continues to carve. So with the first meander, it sets out like a, what is that called? The edge of the river to each side. The edge, which typically there is good agriculture there because there are deposits and so forth, and there's a water source. So a lot of agriculture traditionally has gone on here on the sides of rivers, particularly primitive agriculture, or primary and secondary agriculture. Then eventually the river valley, right? The river valley extends and pushes out to generate a new valley that is below the original valley altogether, because all that sand got all the sediment got pushed downriver, got eroded downriver, On a moment, I think there's some chats here. Oxbow legs, okay, alluvial plains, yes, great, okay. Alluvial, yeah. Alluvial plains is one name, yeah, because it's a reference to, alluvial is also a reference to rain, to rain. And so when you have to put together or combine the river with the rainy season and the dry season and so forth. So obviously during the rainy season, the rivers grow and erode more. And then the dry season, it may go down even to a trickle, or the river may totally disappear in the dry season in some places and then come back. Those are, there's a name also for those rivers that are so seasonal that they disappear in the dry season. Yeah, I think they're alluvial rivers. Anyway, okay, and oxbow lakes, yeah, from these legs sticking out. All right, yeah, floodplains, good. All right, what else? Yeah, so horizontally, the river is also carving its way and eroding out, and that's eventually how we get over the millions of years something as spectacular as the Grand Canyon. Okay, I think it's 1 mile down, more or less. And one has to be careful with pressure here, but also mostly the temperature. The temperature drops a lot. So this is very hot up here. Generally in the Great Plains, I've never been to the Grand Canyon, it's on the to-do list. But as one drops down on these expeditions that go down, it gets colder and colder and colder. And so people up here, you need to take sweaters with you, perhaps several layers of sweaters, because by the time you get down here, I hear it's rather cold. All right, let's move forward. Another characteristic is the surface tension of water, surface tension. All right, I'm gonna have to speed it up a little bit, and because I'm not gonna have time to run through the whole thing. Notice on this diagram, you can barely notice that the molecules down here, this is water in the liquid state, okay? Water in the liquid state. But water in the liquid state at the surface, the molecules are slightly more compacted. They're slightly closer to each other, Look, for example, here, generally you can see more space in between the molecules than up here. You can see less space between the molecules in general, all right? So that means that these molecules are a little tighter together. They're still in liquid form and they're still interacting. In fact, it's a dynamic state where some molecules are leaving the liquid state going into gas, and an equal number of molecules in general are coming into the liquid from gas. Okay, so you have this dynamic exchange of molecules. On average, statistically, proportionally, it's half and half on average over a particular area or surface, all right? But this net effect, the net effect of these molecules being closer to each other is what we call surface tension, All liquids have a particular surface tension, all right? Now, together with a relatively high heat capacity, the heat retention of water, water also has a relatively high surface tension. The surface tension is because of the polarity of the water, that these molecules that are at the surface, at the very surface, that tend to escape out into the atmosphere are being held back by the polarity. In other words, this particular molecule that tends to escape out into the atmosphere is being held back by this hydrogen that is locking into, is magnetizing, is pulling on the ball spot of this oxygen, right? Whereas these two hydrogens are being repelled and so forth. But then this molecule itself is being held in place by this hydrogen and this oxygen, etc. So you have that, it's kind of hard to leave the surface for molecules. It's kind of hard to leave, and that causes a tension, a surface tension, that it takes a certain amount of energy to break. This makes water sticky, and slippery, all right? Other liquids have a much lighter surface tension, and it's much easier to break through the surface of other liquids. I'm thinking particularly alcohol. So you have these bugs. This is called a water strider. And the water strider, you can see, actually can sit on top of water and navigate on top of water and not sink in. That's because we don't see it, but microscopically on these legs, the 3 pairs of legs, 1, 2, 3 pairs of legs, the last extremity has little hairs. They're called CT, all right, little tiny microscopic hairs that increase the surface of the leg, of the foot, if you will, tremendously, immensely. It's the same effect that gives the lizards, the geckos, or geckos, the capacity to move up the wall and across the ceiling, because they have this little tiny hair-like structures that are called CT at the tips of their pads of the legs, of their fingers, and they stick to the surface of the wall, of the ceiling, all right? But here it's because that increased surface does not break the surface tension, Here's another example. You see this swimmer, well, this is an actual photograph. You can see that this swimmer is pushing up the water at the surface. It's a thin surface that is on top of the swimmer's face, all right? And it's bulging. This water is actually bulging up at the surface against the pull of gravity because of the surface tension. This swimmer's head has not broken the surface tension yet. And so she cannot breathe yet because she'll get water into her nose. She actually has to break the surface tension with her head in order to be able to allow the water to slip through her face down and off, at least past the nostrils, so that she can breathe, okay? But the surface tension of water is fairly high, and it allows for water to be walked upon by some insects and other animals. There's a lizard from Central America that can also run on top of water. They run so fast that they don't break the surface tension, and they can go across a pond or something like that by literally running on water, not walking. If the lizard starts walking, they'll sink. But if they run, they can run on water, literally. It also allows water to bead and to bleed off a leaf, if you will, slide off. It's what water is, the sweat of the water that remains around the glass, on the outside of the glass, and not pulled down by water against gravity because excuse me, because of the surface tension. Okay, so that's another characteristic that affects nature. Moving forward, back to erosion. So another little chat here. Let's see what we got. Highly invasive. Yes, the basilisk, right. The basilisk is the name of the lizard. And they're all over the place. They are invasive in Florida, in South Florida, Dade County. I've seen them. I think one student spotted one at our campus one time in our forest, but it's mostly the iguanas that we have on campus. But I have seen them in South Dade, down toward the West Kendall region, this basilisk. You can look it up online. They're kind of pretty, long tail. The tail is at least as long as the rest of the body. Okay. Erosion, look at this erosion by water. All right, the oceanic erosion, the surface erosion is tremendous, is relentless. The tide, but mostly the waves are gonna be pounding and pounding on that rock until they little by little demolish the rock and they turn it into sand, okay? Here's a combination of water and also wind, that when sometimes the sand particles have picked up and they're small enough, and they serve literally as sandpaper. When the wind is moving that sand blown by the wind across the water, but this is mostly the water effect in combination with the wind also, but tremendous amount of erosion. Anyone recognize these? The famous cliffs of Dover, right? On the British side. I think I've heard that if on a clear day, which is seldom up there in the Northern Sea of the Atlantic, on a clear day, you stand on the shores of Normandy on France, you can literally see a little white fringe of the clothes of the Dover, the white cliffs of Dover across the North Atlantic. This is mostly calcareous sand rock that has been eroded tremendously over the eons by the ocean. So we get back to the vegetation, because we have some vegetation, particularly in the tropical regions, that stabilize the coast. Any vegetation that grows naturally along the coast tends to stabilize it. In the temperate regions is more grasses, some grasses that literally tolerate the salt water because they have a mechanism in the root system that is called the active transport system, where they literally suck out water, pure water, out of salt water. Okay, it takes extra energy to do that, but they can afford it because they get plenty of sunlight and metabolize and produce a lot of glucose. But here in the subtropical and tropical regions, we have the mangrove, and the mangrove has to be preserved because mangrove stabilizes the coast tremendously against erosion, And I've seen this happen. You can go down to Mathis and Hammock in the southern part of Dade County, and you can see that where the mangrove is missing, the ocean dips in and the shoreline dips into the sand and all the way to the road. It literally will continue to erode the sand away. And so mangrove is a great stabilizer of the coastline, mostly because the root system that they have, which is called an aerial root system. And again, mangrove, there are three types of mangroves, the red, the white, and the black mangrove. They have also this active transport system on the roots that allows them, the root hairs, which are microscopic, literally allows them to suck pure water, pure H2O out of the ocean, and thus use it for their water, which is basic for their metabolism. And then they will photosynthesize and produce excess glucose that allows them then to invest that glucose into the active transport system of water at the level of the root hairs. Another little chat here. Okay, sea oats, yes, sea oats. But I wonder if the sea oats, so the sea oats are pioneers when we talk about succession, right? We'll get to succession, but sea oats, I don't know if the sea oats can actually tolerate salt water or not, or they go right to the edge, but they stay literally above the tide line. All right, I know that some other grasses do, they go into water. Even there's a grass that is actually adapted. We have on Biscayne Bay, turtle grass. You look up turtle grass, which is Thalassia. Turtle grass has adapted. It's a grass. And you look at Biscayne Bay and there's grass. You know, if Biscayne Bay emptied out, you can take a lawnmower and mow the grass, the turtle grass on Biscayne Bay. It's a grass that has adapted to the ocean and has this active transport system. In fact, I've literally seen when you snorkel on Biscayne Bay, you can see the little flower stalks of turtle grass on the bays.
Okay. Father?
Yeah, Luis?
Yeah, we actually have like 6 or 7 species of seagrasses in this area in Biscayne Bay. Thalassia is one of the most important because it has a thick blade. But we have others tiny and similar, like the Syringodion, the manatee grass, and we have the Hallow Julie. We have several grasses at different depth that provide that stabilization. And one of the problems we have now with the propellers scaring is that because they are perennial grasses, most of them, except the tiny ones, the Halophila decipiens, that they don't recover well after that, and actually the filamentous algae, they take cover and quickly suck up the oxygen from these intertidal zones and becomes like dead zones.
Makes them anaerobic,
That's one of the problems we're having in Biscayne Bay, and of course less diversity, less habitat and food for sea creatures there.
Exactly.
So they are very important for stabilization and for, you know, the habitat, the diversity in
Yes.
that coastal environment.
Absolutely. And I would like to mention also, building up on this, that unlike the mangrove that we can actually see literally, the trees that grow along the shoreline, and thus perhaps a little easier to protect because when they're gone, we can see that they're gone, like seawalls and construction like that, you know, perhaps it's a little bit easier to enforce regulation and to enforce conservation. Unlike that, the turtle grass or the seagrass is below the surface. And so we could see it a little bit from the surface, you know, by patches where it's a little more green than blue on the ocean, but we cannot see it that well. And it's much harder to detect its disappearance, its damage, etc., unless we actually get literally into the water or from above and so forth. So that's another let's say, disadvantage that the seagrasses have against themselves. They're great stabilizers, but they are literally under the surface. Okay, and I suspect that they also go up the coast into perhaps into the temperate region, into the Carolinas, into the Great Barrier Reef, not the Great, sorry, the Grand Banks and the, what is that called, Cape Hatteras, that whole region of the Outer Banks of the Carolinas. So they may, some of these grasses may go up into the temperate region, also maintaining the stabilization of the coastline, right? Okay, let me move forward. Gotta speed it up quite a bit. I may not have chance to finish all this if I make a commitment to 12:30, or as we get closer, I can ask you if you can stay longer. If you have to leave by 12:30, leave, but the video will continue, okay? Okay, so let's move forward beyond erosion. Let's look at the natural composition, the chemical composition of water, natural water, all right? Emphasis on the natural now because I'm trying to move more and more into the natural setting. So what do we have? We have three main types of water naturally regarding their chemical composition. We have either fresh water or salt water, and then in between is called brackish water. All right, so we have fresh water, brackish water, and salt water in general. And then there are nuances of that depending on the amount of salinity, depending on the amount of salts that are mixed in. Now, keep in mind that a salt is like sodium chloride, for example, otherwise known as table salt, of which you shouldn't be using any because food has naturally plenty of minerals and salts in it. So stay away from table salt. It hardens your arteries and could give you high blood pressure, etc. But anyway, table salt, sodium chloride, is two ions that are coming together, sodium, which is positive, and chlorine, which is negative, right? And so they form this stable molecule we call salt. When that molecule goes into water, which is also known as a mineral, it ionizes. In other words, they separate. They separate precisely because the sodium, which is the positive ion, likes to hang around with the bald spot of the water, which is negative, right? And the chlorine, which is negative, likes to hang out with the hydrogens of the water molecule, which is positive, right? And so water ionizes these minerals, these salts, and we get this ionization, the salts dissolve. And that's the difference also between a solution and a, what's the other one? Not a suspension. When minerals in general go into water, they dissolve into water and they stay more or less permanently dissolved into the water column itself. They don't deposit out, right? Whereas a solution, so that's a solution, but a suspension is where the substance that we put into the water will go into the water column when we shake that water, all right, we shake it, but then when we allow the water to sit passively undisturbed, those sediments will come out of the water column and will tend to settle down to the bottom or the top if they are less dense than water, like for example, ground up wood, for example, could be ground up cellulose, will tend to go up, but most substances will tend to go down to the bottom of the water. That's a suspension. right? And that needs to be shaken up periodically if one needs the suspension to be suspended in the column. Whereas a solution will stay more or less permanently ionized, dissolved into the water, because the water coats those ions and holds onto them, all right? So salt water is a solution of more salty water than fresh water. And the way it's measured is the scale that is used generally is this PPT is an acronym for parts per thousand. How many parts per thousand of minerals are dissolved in water? All right. And I can tell you that natural water, seawater, from having saltwater aquariums and all that, has about a dozen different salts. And yes, you can literally buy saltwater crystals in a bag at the aquarium shop. All right. And it's a bag of white powder that is very salty, but it's not just sodium chloride, because the animals and the plants living in the ocean need the other minerals too. So it's about a dozen different minerals that are dissolved in salt water, between the positive ions that are called cations and the negative ions that are called anions. All right, here's the table. It's about a dozen of them, and they have different parts per thousand, or parts ppm will be parts per million. In other words, milligrams per liter dissolved into the water. But the overall, we can look at the overall solution of minerals in the ocean, and that is this overall PPT, parts per thousand. And we can say that the overall saltiness of fresh water is less than 1 part per thousand, about 0.5 part per thousand. All right, that's fresh water. In other words, fresh water naturally has minerals. That's why also we should not drink pure distilled water, because when we drink pure distilled water, it sucks out the minerals from our body. It leaches our body. So pure distilled water is not good to drink in any large amount, but the natural normal water that we drink, including the tap water, which I've been drinking from Miami for about half a century and still living, it has all the minerals that we need in the body necessarily, all right? And so also stay away from bottled water altogether, because of all those plastic, single-use plastic bottles that are a real mess to take care of. All right, at the opposite end of that is salt water, which the average is about 35 parts per thousand. 35 ppt is the average solution, mineral solution of water, of salt water. And that's why it tastes salty in the ocean, etc. In the middle, more or less, it's going to be brackish water. So anywhere from 0.5 to 17 ppts, 17 ppts, about halfway, is brackish water, about halfway into the salinity of water, all right? Brackish water is a mixture, and typically in nature, we find them in estuaries or deltas. In other words, when a river of fresh water mixes with the salt water in the tidal effect of back and forth, and we get the brackish water. And that is a particularly rich environment for microorganisms, and then all the food chain that follows from there, plants and animals that live in those areas. And they are, many of them are restrained and restricted to that brackish water, because that's the range of tolerance of saltiness. And if it gets more salty, they start dying off. So they live typically, and they're restrained to living in the brackish water in the estuaries of rivers throughout the world. Then when we get into the ocean as such, the nice blue ocean, deep blue ocean, the average rain is 35 ppts, but it can vary, all right? It can vary from almost brackish water, which is the Black Sea, because the Black Sea, you see, is there in the middle of Russia, and it is actually in the border, I think, between Russia and Turkey somewhere, and it is totally landlocked. And because it is landlocked, it is losing its salinity. Why is it losing its salinity? Because of the rivers that empty into it, and those rivers come from mountain ranges around it and come from rain, which is essentially less than 0.5 ppts, all right? Rain is almost pure water, not quite, because it does pick up stuff along the way down, but rain is dissolving the Black Sea, and turning it into basically a lake, all right, of fresh water. So you can see it has the high end of brackish water PPTs. On the opposite end of that is the Dead Sea, which is also landlocked and is disappearing, and is in Israel, I think between Israel and Jordan, right? You can look it up. But the Dead Sea is also disappearing, but of the opposite effect. The opposite effect is that instead of getting plenty of rain from rivers, it is disappearing. It only gets a trickle of water from the Jordan River, which is locked. What do you call that? Una represa. It has a dam. It's dammed, right? Literally, not figuratively. So the fresh water that's coming from the Sea of Galilee, which is the main freshwater source for all of Israel, right, with strategic implications, the Israelis retain the fresh water up in the Sea of Galilee, and so they have dammed and locked off the Jordan River, so it's just a trickle coming down into the Dead Sea. But because it is in a near, I guess, temperate region, but gets plenty of sunlight, and it's also below sea level, it's evaporating. It is evaporating away, and so that it is now actually split into two parts. The shallow part only has about 5 or 6 feet of water left on it, the Dead Sea, and it's gradually disappearing. The end result of that is that the salt concentration has increased tremendously to about 10 times more, to 337 ppts as opposed to 37 ppts, which is the normal range, 35, the normal range for salt water. So the Dead Sea is about 10 times saltier than the average ocean. It makes it actually viscous. It is thick. It is thick like baby oil. It is transparent because nothing lives there except from some extremophiles. We talked about extremophiles. They are extreme bacteria that like these extreme environments. They're extreme halophiles or halophiles that like very, very salty region. That's about all that there is there, and that's why it's called dead, because it is essentially dead. No other living creature can live inside of it, literally, not even humans. And when you go into the Dead Sea, I was privileged to go there once on a pilgrimage, you have to be careful. If you have any little tiny nick or cut on your body, you're going to feel it right away because it's going to burn, sting like you're putting lemon on it. It's very, very salty, and you can actually float standing up. You can float and bob standing up because it is so thick and so dense. Okay, that's Dead Sea, and it's because of the extreme salinity it has, and mostly because of evaporation. All right, moving forward, this range of salt water, on average 35 ppts, allows for the ocean to be fully alive with plenty of plants and animals and bacteria, all the way beginning with the phytoplankton, the beginning of the food chain, all the way up or down, whichever you want to go, to the largest creatures on Earth, which are the whales, marine mammals, some of which actually feed on the plankton, on the krill, which are little tiny, what are they called? They're shrimp-like creatures, that and the humpback whales feed on them, for example. So you get the largest animals on Earth feeding on the smallest animals on Earth, and that's all in the ocean, all because of that particular salinity adaptation of the plants and animals that live in the ocean, which is where we have the highest biodiversity by far on the planet. Okay, so speaking of the oceans, then let's look at some ocean currents, staying with the hydrosphere concept and kind of expanding out to the big picture. Let's look at the currents, all right? Again, natural water on Earth, how it's happening, mostly on the oceans. Let's see, by surface, it's about 3/4 of the ocean. I think about 75% of the surface of the Earth, 75%, about 73% of the surface of the Earth is water, is ocean. All right, that means that only about 25% is land, dry land, where we live. And most of that dry land, like I mentioned, is above on the northern hemisphere. But volume-wise, that's just surface. Volume-wise is more than 90%. 90% of the crust of the Earth is the oceans, all right? It's the volume of the oceans themselves. So some people have made the case that our Earth is misnomered. It should not be planet Earth, it should be planet Ocean, because mostly by surface and by volume, where we live, certainly where we have the biosphere, is ocean, okay? It's saltwater environment. Okay, so this ocean is also in a dynamic state, very interesting dynamic, and there are two motions going on. There's a general horizontal motion of the ocean water going around, all right? 6 large currents that occur throughout the whole planet, 6 large currents. They're also known as gyres, and that's the technical term for them, 6 gyres that occur. Let's point them out. There are 2 gyres in the northern hemisphere and 4 gyres in the southern hemisphere. So we have, the easiest one to spot is the North Atlantic gyre, all right, which by the way goes clockwise. So the currents, the ocean currents in the northern hemisphere generally go clockwise, and in the southern hemisphere they go counterclockwise, kind of backwards to the wind pattern or the Coriolis effect on the wind pattern of the atmosphere. At any rate, the North Atlantic gyre, as you can see here, rotates this way, okay? And it's particularly interesting for us because it picks up on the Gulf Stream, which is this little one here. And the Gulf Stream builds in the Gulf of Mexico, comes out through the Straits of Florida, which are between Cuba and the Florida Keys, and then meanders up the coast, the Gulf Stream, off the coast of Florida, including Miami Beach there. You can stand on a clear day on Miami Beach and look out east, and you'll see a bunch of white clouds on the horizon, the large cumulus clouds on the horizon. Those are kind of trailing and they're following on top of the Gulf Stream, which has been described as a saltwater river in the ocean. A warmer water that moves up generally anywhere from 3 to 5 miles an hour. So it's significant. And if you're cutting across on your boats, you have to adjust for that. Otherwise, it'll take you much northern latitude that you were planning on arriving or landing. Anyway, the Gulf Stream unites with the rest of the North Atlantic gyre and eventually goes across the North Atlantic into the coast of Ireland and veers down, bringing warmer water to Ireland, and that's why it seldom snows in Ireland, and you have a more benevolent climate, but there's certainly plenty of rain because this North Atlantic current here is bringing warm air with it, with the warm water that is riding on top of it. The warm air is moist and dumps, when it hits on land there with Ireland, it impacts with a cold land mass and condenses and makes it rainfall, all right? But it also keeps Ireland unseasonably or by its geography keeps it warmer than it's supposed to be by geography, all right? Because other countries at that latitude in northern Europe are much colder, all because of that current. So it has an effect on the biota of the geography. Then as it reaches those northern latitudes, it cools down and comes down as a cooler Atlantic current across what is essentially Portugal, the coast of Portugal, and then down into the Saharan Africa here, Canary Islands and all that. And as it reaches near the equator, it warms up again and continues to gyre, to twist and turn clockwise, making that North Atlantic gyre. We have the opposite effect in the southern hemisphere, by pretty much again by the combination of the Coriolis effect, which is, the rotation of the Earth as the Earth is rotating eastward, right, spinning. Then the same gyre forms in the southern Atlantic, but in the opposite direction, okay? And so it will twist this way in the southern Atlantic gyre, picking up, coming down the equator through the coast of South America, bringing generally warm waters down through Venezuela and mostly this guy here is Brazil, and then Uruguay and Argentina, and then being pushed by the Antarctic stream up against the coast of Africa, which will actually make the south western coast of Africa a little cooler than it would normally be by geography, because it's picking up that cold Antarctic current, all right, until it reaches up into the equator, warming up at the equator, and then coming down again. So there's mixing going on with these gyres. What these gyres do is they mix. They bring up not only water, but sediments from Antarctica, for example, and recycle them into the Northern Hemisphere. And by the same token, you can think of these as two figure eights, picking up sediments from the Northern Hemisphere here between Greenland and Europe, and bringing that down through the equator into the Southern Hemisphere. So there's kind of a figure eight circulation here of not only water, but also sediments, microscopic and suspended in the water column, and also the biota that goes with that, the plankton, and then the animals that follow, etc. We also have two big gyres in the Pacific. Well, before I go there, let me just go for the sake of progression here. If we move eastward along the Southern Hemisphere, we have the Indian Ocean. So there's an Indian gyre here. There's an Indian Ocean gyre that you can see. Sorry, going the wrong way. Starting at the equator, let's say, here's India, right? And this is known as the Indian Ocean. So at the equator, it picks up warm water, moves south along Madagascar, the island of Madagascar, and the southeastern coast of Africa, down, picking up again into the Antarctic current that is moving eastward, and will move up the coast of Australia, across the Southeast Asia here. I guess here is, what do we have here? Singapore in that area. Here's the peninsula of Vietnam. There's another little tiny gyre that forms in there. It's a counter gyre because you see it's already in the Northern Hemisphere, one to each side of India. This is the Indian Peninsula here. Anyway, so we have this fairly large Indian gyre, Indian Ocean gyre, contained in the Southern Hemisphere and flanked by the equator, Southeast Africa, Antarctica, and Western Australia. And then we get into the Pacific, that you have to kind of connect this section with this section. Is split in half, the Pacific here, but we have two large, huge, the largest gyres on Earth are the Pacific gyres. And again, there are two, just like in the Atlantic, there's a Northern Pacific gyre that turns clockwise, and the Southern Pacific gyre that turns counterclockwise. All right, and these currents are extremely rich with nutrients. They make the western coast of North and South America very rich in plants and plankton and animals, also because of the upwelling of minerals from the bottom and so forth. But it does the same out here, whether it's the Northern Hemisphere, the coast of Japan, the Japanese archipelago, and then further down south, you got the other one, this other huge archipelago of the Philippines, and then you get into the Polynesian Islands in the Southern Hemisphere. All these regions are very rich in fish because they're rich in nutrients, and they're rich in phytoplankton and zooplankton and other food chains that established there, okay? So these two gyres are the largest ones, the Pacific gyres, north and south. You've heard about the great garbage patch, the great garbage island and patch of the North Pacific gyre. We'll talk about that later, a few lectures down, but it's formed essentially here. But it's kind of an invisible island, transparent to the eye, to the naked eye, because it's mostly small fragments of mostly plastic and other debris that is floating around there, even all the way down to the microscopic level, but down to the particle and bottle level. We'll talk about those later when we get into the pollution. Okay, so much about the gyres. It's a Coriolis effect, which we covered earlier for the atmosphere. It also occurs in the oceans, and it keeps the ocean circulating. So all of these gyres connect mostly in the southern hemisphere by the huge Antarctic current that generally moves eastward below and around the Antarctic continent, okay? So this is a good segue to introduce the topic of the poles, because we have two poles, which are solid water on the top, on the surface, right? But then there's a drastic difference between the two underneath the surface. So let's talk about Antarctica first, since I was there, not in Antarctica, I was there lecturing, talking about it. In other words, here is that the Antarctic current generally goes around Antarctica in a clockwise fashion, all right? And affecting, here would be the South Atlantic gyre, right? And then here would be the Indian, this is the tip of India here, this is the tip of Africa, tip of India, I guess, or maybe it's Australia, I can't, no, I guess this is Australia. So here would be the Indian gyre, yeah, okay. Yeah, this would be the Indian gyre here. And then this would be the Southern Atlantic gyre, okay? Southern Pacific, sorry, Southern Pacific gyre. So he would have the Southern Atlantic gyre, Indian gyre, and Southern Pacific gyre, all right? And they're all going around the Antarctica, which is a continent. In other words, there's a land mass underneath. In fact, it's a plate. It's a plate. And you can see just graphically by the pattern here, how this is partly erosion, but also the rubbing of these tectonic plates and the shifting of the tectonic plates. Just from the eye, it looks like the plate itself of Antarctica, it's kind of rotating counterclockwise, and the plate of South America, which this is South America, is also at least moving. Maybe they're not rotating, but they're moving westward, and they've lagged behind a segment here of a ridge, which is in the Southern Atlantic, and they've left it behind. So you get this effect of a pocket that has formed in between these plates. Very interesting geologically what's happening down there. All right, very slowly, but really these plates can move up to maybe 1 to 2 inches per year, like the North Atlantic and here the North Atlantic, the European plate and the North Atlantic plate are diverging or moving away from each other about 2 inches a year. Okay, so that's pretty significant. We can actually measure it in centimeters per year. At any rate, what I want to say this. So Antarctica, which is solid ice on top, of course, all right, and a continent underneath. In contrast to that, in the North Pole, we do have solid ice at the North Pole, and then Greenland, which is now melting, all right, but Greenland is, well, considered an island, a very large island, but it is a continent. In other words, there's landmass underneath. But the very North Pole itself, what we know as the Arctic Pole, right, is a little cap of ice. It's like a humongous ice cube that is sitting there on top, kind of wedged in between North America and Eurasia here. So in political geography, on the North America part, we have essentially Canada, and in the Eurasia, we have essentially mostly Russia, and then some of Scandinavia here, sorry, here, all right, but it's mostly Russia over here. So the North Pole is, you can think of it as a humongous ice cube that is being held in place by Canada and Russia. In place, but it's an ice cube and there's no continent underneath the North Pole, all right? And this was proved back in 1958 or 59, the submarine Nautilus, the Nautilus submarine. Why? Because this was the first time that we had a submarine that could literally travel underneath the North Pole through, from the Atlantic to the Pacific, all the way through underneath, unencumbered, not hitting, not crashing into a continent like Antarctica. Because in Antarctica, if we try to go through Antarctica, we're going to crash into the continents on any side. But the North Pole, as solid as it is, okay, is underneath is liquid. It's the North Atlantic that meets with the North Pacific. And that was proven. And why the Nautilus? Because this was the first nuclear submarine, all right? And the first nuclear submarine had enough power to take this trip, which I don't know how long it lasted. Actually, you can look it up if you want, but it had enough power to allow it to go unencumbered underneath from the North Atlantic to the North Pacific without crashing into the Arctic continent, which doesn't exist. All right, so that's the proof of principle, if you will, that this is a huge ice cube that is sitting there, and it's slowly melting away because of the seasonal change of heat and cold and so forth. We'll talk more about it when we talk about climate change. All right, back to land. I want to talk a little bit about glaciers. As I mentioned, the glaciers have a tremendous erosion capacity. As you can see here, here's a glacier that has receded, all right, and melted away and left underneath, I think it's called a moraine. It leaves behind all of this erosion, barren rock that has been carved out of the mountains, the mountain range. This may be, it could be any of the large ones. This could be probably not the Andes, it's too wide. Maybe the Rockies, maybe the Alps also looks a little too wide. Himalayas or the Rockies somewhere. But anyway, we have a glacier that is advancing in this photograph, right? Pushing very slowly over the thousands of years. This moves very slowly, a few inches, a few meters forward in accumulation of ice at the top of the mountain, pushing down, buried mostly by gravitational weight, pushing down on the head of the glacier. So here's an advancing glacier slowly moving down. Here's a receding glacier, all right, because it's a balance between the amount of snow that falls on the snow caps and eventually trickles down and pushes down on the glacier. That snow, actually compacted snow that built on the top of the glacier to push it down, in contrast with warmer season that melts the edge and pushes the glacier up, in the sense as when it's melting the edge or the head of the glacier, and thus receding that glacier because there was more dry, warmer time over periods of seasons. Overall, the slope of the line, would have been a negative slope temperature-wise, and the glacier recedes. But if the glacier is advancing, then the slope of the line over thousands of years or hundreds of thousands of years would be a positive slope. In other words, there was more deposition than evaporation, all right? And so we look at a graph here, and I want to point, this is important. That's why I'm going to go beyond the 12:30, folks. If you need to leave, go ahead. Don't worry about it. I'll continue recording, and you can watch the rest later, okay? Or you can stick around. It's up to your schedule. But I do need to push forward because look at this. What do we have? This graph here, look at the scale, first of all. Only less than 500,000 years, okay? This is in the past 500,000 years, about 450,000 years, less than 1 million years, 500,000 years, Now the Earth has 4.5 billion years, right? And each billion is 1,000 million. So this is very recent, relatively speaking of the age of the Earth in the geosphere. This 500 million years is not that long ago. Of course, for the human scale, it's humongous. It's humongous because here we are today on this little tiny clip here, all right? So 100,000 years is long. This could be the age of the beginning of Homo sapiens could have been here. The past 100 to 200,000 years, if we take the short range, if we look at the genus of Homo as such, we would go 4 times over, right, to about 2 million years from the fossil record. But sapiens, the past, actually, Homo, the genus Homo, in this range, 100 to 200,000 years ago, okay? So just to have a sense for the scale, what do we know from the evidence of the ice and ice cores and ice profiles and so forth that have been done, natural ice, either on glaciers or rocks, and the erosion? This is indirect, but this is very strong evidence of these glaciers advancing and receding, all right? We not only can go horizontally on it, but we can also go vertically up the mountain range and interpret the layers of sedimentation that have formed over the eons along the mountain range as we go vertically up or down the mountain. And we get these profiles, we get these strata, and there have been at least 4 major ice ages, that would be below freezing, above and below freezing. Now look at the scale. Here the scale is in Fahrenheit. And so freezing is around 30, right? 32 degrees Fahrenheit is freezing. So the scale is Fahrenheit. So here is freezing. Anything below is freezing. The ice, it's called the winterization of the Earth. When the Earth as a whole has frozen over, all right, the land masses. The oceans have remained liquid, mostly because of the salinity, which has dropped the freezing point. But the land masses on Earth, in other words, we have mostly fresh water. That water has frozen. And we have these 4 major ice ages, right? Or otherwise known as glacial periods. So here's 1 dip, 2 dips, 3 dips, and 4 dips, okay? So these 4 dips, looking at it broadly, here's 1. We can draw generally a sinoid curve going up and down like this that has 4 peaks, so 4 crests and 4 troughs, all right? And so each trough, each dip is an ice age. And then when it comes above 30 degrees, above freezing, which would be this one generally, I know that this has kind of a double dip here, and then this one, and where we are today, these 4 above freezing areas, okay? This is called the tropicalization of Earth. So just in the past 500,000 years, when we look at this graph and we interpret the big picture, we can say that the Earth has gone through 4 cycles, at least 4 cycles of winterization, where it has been mostly winter, and again, mostly in the northern hemisphere, to tropicalization, where it has been mostly a tropical environment or subtropical environment, again, mostly in the northern hemisphere. 4 times we have to have this cycle back and forth, all right? Back and forth. And there seems to be a certain repetition here. There's a cycling. So by using statistics, the stuff we hate, we can project based on the past, which goes back to 500,000 years ago. Based on the past, we can try to project, you know, if we take this sinoid curve that is upping and downing, and we project it forward, we could project it forward with the same cycling more or less, produce replicate the same cycling, the same periodicity forward, all right? And it would seem as we were naturally heading toward another tropicalization. And then eventually in a few 100,000 years, we dip down into a winterization and then back to a tropicalization and winterization and so forth. But generally, you know, we're just barely above, on average, barely above freezing, okay? So it's anybody's guess which way we're heading naturally by this natural cycling, either to another tropicalization, or it could be this is actually a low crest, like it was here and maybe here, as opposed to a high crest here and here, and we could be heading down back into a winterization on the other side. Anybody's guess what's going to happen in the next few hundreds or to thousands of years to tens of thousands of years. But you notice the scale is minimally in the thousands, more comfortable in the tenth of thousands, and even more comfortable in the hundreds of thousands of years, okay? So when we're down to measuring weather as opposed to climate on a yearly basis with a thermometer, all right, and even after decades or maybe a century or 2 centuries, I mean, how far back were people using thermometers, right? 100 years, 200, 500 years, barely, maybe, probably since the Copernican revolution or the scientific method about 500 years ago. It's a very tiny scale, all right, when we have systematic data of temperature to see any possible trend. Beyond that, if we go into the thousands of years, we have to look at indirect data. In other words, the sedimentation rates of what sedimented and how fast it sedimented and so forth, to try to figure out, deduce from current evidence of deposition of the ice ages, okay? So certainly beyond a few hundred years, this scale is from indirect evidence. But it's fairly reliable because of the ice cores that are used and so forth, all right? And the actual dust sediment that is found in those ice cores, etc. Okay, but just this to point out that the Earth has naturally cycled from winterization to tropicalization, which is pretty drastic as far as the animal and plant population and bacterial population, the biota population on the surface of the Earth, back and forth between being very, very winter-like environment throughout the whole Earth, particularly the Northern Hemisphere, to being very, very tropical throughout the whole Earth. Again, mostly the Northern Hemisphere where most of the landmass is located. Okay, this data, store in your mind, put it back there because we're going to use later when we talk about climate change and global warming and so forth. We have to essentially figure out from this, what is the anthropogenic effect or contribution of global warming to the Earth. Anthropogenic meaning generated by the human, created by the human. In other words, mostly fossil fuels, the increase in CO2 from burning fossil fuels, all right? Because we can see that these peaks happen naturally, all right? Total tropicalization of the Earth, and we had absolutely nothing to do with it. At some point, we weren't even existing as a species. And certainly, we did not have the capacity of the Industrial Revolution to produce the CO2 that we're producing today, just by burning campfires, all right? Okay, we'll get there. Back to the volume of the Earth. I talked about this. The volume of water on Earth, volume of water, just to get a feel again for that volume, bringing it all the way down to from liquid to the gas component. If we look at the liquid component, it is mostly ocean. So it is mostly salt water, all right? Mostly salt water, except for about 3%, which is fresh water. Brackish water is very, very tiny compared to these percentages, okay? But it's mostly ocean then. That's why I said that most of the water on Earth is the oceans, and it's at least 90% is actually a very large volume of the water is just oceans. But this 3% of fresh water can be further subdivided if we excuse me, if we take this 3% as a total, a new total, a subtotal, okay, then we have that most of it is in ice caps and glaciers. So most of the water on Earth is taken up by ice caps and water, most of the fresh water. And of that fresh water that is available, so ice caps and glaciers are not available, right, for life, not available because you have solid ice, solid, no metabolism is going to occur there. From that, almost 80%, the 20% that's left over, okay, 20% is mostly underground, again, not on the surface of the Earth. So there's very little water that is available on the surface of the Earth for metabolism, for keeping us alive. And so most of it is salt water, which is not inside the animal or the plant. Then there is groundwater of the fresh water. Then there is about 1% of the 3%, okay, is liquid water that is on the surface of the Earth, on the surface. And of that, at least half of it is lakes, right? It's in lakes. Then about 40%, the other almost half, is moisture that is trapped in the soil, moisture in the soil. And this is good because this is available now for plants. This is a moisture that's available in the soil for plants, finally, for metabolizing, for absorbing that water through the water vascular system up to the leaves so that the leaves can photosynthesize and generate glucose from that water in combination with carbon dioxide from the atmosphere to make glucose, which is the energy molecule of nature. And a side product of that reaction is, guess what? Oxygen, the oxygen that we breathe, all right? So plants sink CO2 into the earth by making that glucose, and also the plant tissue itself indirectly, and release as a side product the oxygen that animals need for living, and plants also, because plants also respire, plants also use oxygen for living, for their own metabolism. Anyway, what's left over of this liver here, when we take out 50% and 40%, is about a 10% that's left. That 10%, about 8% of it is water vapor. Water is just evaporates right now through our skin and everywhere else. Every animal, every plant is evaporating water. Okay, so it's lost out to the atmosphere, back out to the atmosphere. And then from the 2% of the 1% of the 3%, finally that 2%, 1% of it is with living organisms, and the other 1% is all the rivers of the world. Okay, so more or less we have in the plants and animals of the living organisms, and we have to include here also the marine plants and animals, right? All the water that we are actually holding inside of us is kind of equivalent, roughly equivalent, to the amount of water that is in the rivers of the world, of the local water of the rivers of the world, which is about 1% of 1% of 3% of all the water on Earth. So bottom line, with very, very little water, we have life on Earth. You know, with very, very little tiny amount of water, we have life on Earth. And this is just, to me, is a cause for awe and wonderment that this molecule is so magic, that it has these properties of its polarity, its heat retention, its surface tension, etc., that in combination with just the right distance from the sun makes for the possibility of liquid water, which then makes for the possibility of life as we know it on Earth, organic life, okay? And therefore, we should have our utmost respect for water and try to preserve it as much as possible, because look how little tiny amount we need, but we definitely need for survival. Because if any of this gets altered up the 3 layers of decimals, right, then we're literally up the creek without the water, not without the paddle, but without the water. And without the water, we're not going to survive, and nothing else is going to survive. So we need to be extremely respectful about water and try to preserve it and preserve it clean and so forth. So with that, I'm going to wrap it up now, go into clean water. As recently as 2017, and I was fascinated by this because, you know, this program started, this Masters of Bioethics at St. Thomas University. I launched it after many years of thought and reflection and dragging my feet. I launched it in the fall of 2016. That was the first cohort, all right? You folks are the fourth one. And so in the fall of 2016, I launched this Masters. And by the time we get to the winter of 2017, we have Pope Francis organizing a major conference on the human right to water at the Vatican, all right, at the Pontifical Academies of Sciences. So I thought I was just music to my ears because I could incorporate this data into the program and into this particular lecture, because I was about to, at the end of the spring semester, I was going to cover this environmental bioethics course, all right? So let me back out for a moment and just say that all the modern popes have spoken about water, the importance of water and the right to water. And I'm talking about drinking water, but even just cleaning water, all right? Because the numbers are staggering and staggeringly sad. The contaminated water, the polluted water that many, many people of the world have to deal with, okay? So again, going back to Pope Paul VI, so we start what we call the modern popes. Yeah, I guess we can start with Pope John the 23rd. I'm ancient enough that I remember John the 23rd as a little kid, because he died around 50. No, he died actually in 62. Oh yeah, so I was 10 years old. And John the 23rd was very John the 23rd started the Second Vatican Council in 1962. Okay, that was a big event. I remember we were living in Mexico City at the time, and the Mass almost overnight changed from Latin. So my brother and I were a little altar service at that time, and I always got the bells wrong because I didn't know a hoot of Latin. But Mom had us as altar servers, and I always rang the bells at the wrong time because I didn't know what the priest was saying or doing in Latin. Facing the wall, I was behind him. Anyway, that was Second Vatican Council was started by John the 23rd, and then in a few months later he died, and then Paul VI took over. Paul VI, which was known as a very intellectual pope, and he moved forward the council until finally it was concluded in 1965. Okay, at that time, Carolus Wojtyla was a cardinal of Krakow in Poland, and later became John Paul II. Okay, but in between, I should have put here John Paul I, who was also an Italian pope, Albino Luciani, who only lasted 33 years in the papacy. So talk about a high-stress job, no question. The poor man only lasted 33 days, and he died. But he was John Paul I. The reason for the name, no, don't go there. At some point, I'll have more time to talk about the names and how symbolic the names are. But anyway, all of the modern popes have spoken about water with some degree of urgency, right? Here is Paul VI. Here is John Paul II with his very dear friend, Mother Teresa, okay, when they were younger, somewhere in the world. And here is Pope Benedict, meeting with Pope Francis. So obviously here he's retired already, he's emeritus, and this is the reigning Pope, so we don't have a schism, you know, we don't have two popes and we don't have an anti-pope here. He retired legitimately, it hadn't been done for centuries, but he did it, and it's a legitimate thing. And so here's Pope Emeritus Benedict and Pope Francis. All right, early on, when they were making the transition, this is a meeting they both had early on there in Castel Gandolfo. And here is Pope Francis addressing the Pontifical Academy of Science for this international conference on the human right to water. You know, Pope Francis is very big on human rights and the poor, disenfranchised, because it is truly a huge, huge issue and problem and tragedy that we have today in our world, that many, many, many people of the world have to spend their youth going to the river or going to the lake or going to the pond, contaminated, picking up water and carrying that water home. They start early in the morning and they make trip after trip. And that's what they do basically all day long for their youth years to survive. And many of them are women. So this is a tragic reality of a world where water is scarce and is becoming more scarce. I'm talking about just water for cooking, water that's going to be boiled so that it can be drunk, right? For cleaning and for drinking, let alone potable water. In other words, potable water that is that we can drink. You know, even cities of the world that are civilized, supposedly, they don't have potable water. I remember one time I took a trip down to Brazil. I visited South America, and in Rio de Janeiro, I was very, very thirsty after a day of running around and didn't have access to bottled water. So I just drank just one glass of water from the tap because I was dying of thirst. Immediately, like a flash, I got the runs. I had to run literally to the toilet because I got diarrhea and vomiting just from drinking a glass of water from the tap water in Rio de Janeiro. And later I was staying in the clergy house and I commented it to one of the local priests and says, don't you ever do that again. Okay, you make sure you get the bottled water because it's not drinking water. In Rio de Janeiro, 10 million people, you know, and they don't have drinking water out of the tap, but we do. And so we are very, very, very privileged, right, by having drinking water, and therefore we have to exercise this responsibility for water. Don't let it run. Don't let it run. Even when we're showering, when we're brushing our teeth, you know, turn off the water. When we're washing our hands, turn off the water. When we're washing dishes, we need to be very, very responsible about water, because most of the world, the 7 billion people we are, almost 7.5 billion people, don't have access to water, to running water, let alone drinking water, okay? They have to wash in rivers, they have to wash in contaminated water, their clothing, their bodies, the drinking, they have to spend hours daily boiling water to make it drinkable, and so forth. So, big responsibility there. I'm going to include in my attachment today a statement from Pope Francis on the human right to water that we need to promote. We can say that water is becoming liquid gold, essentially. It's becoming liquid gold. Already there are states and countries that are fighting for water. I mentioned in passing the famous Sea of Galilee, which is also known as the Lake of Gennesaret in Israel, in northern Israel, is the drinking water for all of the, is the source of fresh water for all of the state of Israel, and it's right up to Jordan and I guess Lebanon on the northern side. And if that water gets contaminated, that's the end of the state of Israel, okay? And so there are strategic things that are done for them to save, to protect that source of water and so forth. states. Some states have a lot of water. They sell water to the adjoining states, to the adjacent, to the neighboring states. Other states in the United States or in the nation, also in the world, countries fight for water. They take water from each other. They sell water to each other. They need to buy water. So water is a big, big issue, and we need to take it seriously. A little, yeah, the Golan Heights, Syria. Thank you. The famous or infamous Golan Heights, and that's why during that 3-day war of Israel against, I guess it was Syria, they went in, Israel, and took an extra slice of the Golan Heights to preserve the sources of fresh water that come from Mount Hermon, I think it is, down into the Lake of Gennesaret or the Sea of Galilee, to preserve the sources of water, of fresh water that filter down into the mountain. That's the whole issue about the Golan Heights. The source of fresh water for the entire state of Israel, which is actually in Syrian territory, or was in Syrian territory. Enemies, lifelong enemies of each other, politically speaking. All right, so a lot of issues with water. Let's do good stewardship of it, protect it, save it, and promote it. And we need to promote that among our family and friends, okay? To be very, very responsible, conscientious about our use of water, because we are immensely privileged to have potable drinking water coming out of the tap whenever we want it. Okay, I'll close with that. Look at the statement of Pope Francis that I sent you. You don't have to give me a separate summary of the statement, just incorporate it into the statement of the lecture itself. And also the fact that you will probably get 2 videos, 2 links to 2 videos because of the split that we had earlier at the break with the filming. All right. Thanks again. That's all I have for today. Any parting comments or questions from anyone? No, I hear nothing.
Thank you, Father. Have a good day.
Okay. Thank
Father,
you.
everyone.
Thank you very much. God bless. Stay safe. We'll be in touch.
Goodbye.
Summary Wednesday, as always. Okay. I'm gonna
All right.
the session. All right.
Bye.
Let's see. Stop.